So I'm suspecting I'm facing an audience that has no experience at all in floor heating and wants to know a little bit more about it, all the way to super pros that spotted the word advanced and want to know a little bit more about what they've been doing for years and years. So to that effect, I'm going to talk about three key topics. How heat works, and that's very important because we talk about heated floors as a bathroom luxury, and hopefully I will be able to make the point to you that heated floors is a heat source. Second, we're going to talk about the benefits of floor heating. Obviously, I'm paid to tell you it's a great product, but on the flip side, I want to show you how it compares with other heating systems and what the benefits are. So if you're a specifier or a designer, how you can use floor heating not instead of another heat source, but alongside another heat source. Understand what the benefits are to the purposes of your project. And finally, we'll talk about practical design solutions, how you could use it, what you could walk away with today. How heat works is the first part. So we're going to do a little bit of physics. I promise this is all plain English. I want to get you to the heating side of heated floors first, where we're going to talk about heat loss, heat transfers, and then the various heating systems. Now, heat loss, why we talk about heat loss? Because many times when we talk about heat, we talk about heat gain, heat input. Output here is basically the wattage, but heat input is what you put into your house. Your furnace is a heat input, your baseboards, your radiators, your floor heat are heating inputs. If you live in a passive home that's really well insulated, then people, dishwashers, computers, they're all heat inputs, because they provide heat, they add heat to the space. But the amount of heat you put into a space is only relative to the amount of heat you lose from the space. So if your house is a traditional North American dwelling, it has a medium to low level of insulation. If it's an older house, it probably has none at all. If it's a very modern house, it might have a lot of insulation, but you're probably in the middle of that spectrum. And because of that, your windows, your roofing, your structure, your walls, and of course, pertinent to our presentation, your floors will lose some of that heat. Actually, for floors, it's about 10 to 20%. It could go all the way to 60%, depending on what type of floors, if you have a crawl space. So it's important to know that, because when we design a heating system for a house, or we help engineers specifying floor heating into a building, not just as a primary heat source, but as a secondary heat source, we want to know how much you're going to lose so that we know how much you can put in. There are complex formulas to do that. If there are specifiers on the call, they will be very familiar with a lot of these formulas and calculations. For those of you who are not specifiers or engineers, don't drop off just yet. I'm going to simplify it for you. Essentially, when you put heated floors on a floor, that floor will either be 3/4 ply or it will be a cement slab. That's just about most of the systems. Of course, you'll have hardy backer and cementitious backer boards, and those boards will act as plywood for now for our purposes. So on uninsulated plywood, you're going to lose about 2.5 watts per square foot. And this is how heat loss is calculated. It's calculated on a wattage per square foot per hour, actually, but on a wattage per square foot. So if your floor heating system is, say, 10 watts per square foot, which is on the low end, but relatively average for the industry, this equates to about 35 BTUs for a hydronic system. But 10 watts per square foot, that means that when you put it on plywood immediately, and this is the only thing you need to remember, immediately you're going to lose 25% of that to the plywood. So that's important to know. Most manufacturers will over-design the system because they already know you're going to put it on plywood. They assume your plywood's uninsulated. So your system is going to be expected to lose a bit of that. That way we could put 7.5 watts back into the room. But if you put that same system on an uninsulated slab in a basement, for example, you're going to lose 6.5 watts. So you're going to lose a big proportion of that heat, and you're not going to get enough, as you can see from the graph, to actually heat your space. So heat loss is very important because it defines how much heat input we need to put into the space to actually heat it. That is the same whether it's a comfort heat or primary heat. Usually for comfort heat, you don't have to worry about it. These bathroom systems are over-designed. But if we're talking about a sunroom, a basement, or the whole house, we need to be a bit more specific because we don't want to over-design that system. When you talk about heat loss, you're going to talk about R values and U values, or U factors. Those are two things you might have heard. If you're not familiar with them, they can be complicated, but they are pretty simple in and of itself. The U factor is usually and pardon the vulgarization here, but usually the U factor is about a product, a particular component. The R value is about the system. So there will be a U factor for drywall, a U factor for your siding, a U factor for your moisture membrane, and that will give your wall an R factor. And so you'll have a wall that has an R value of X. So the R value of that wall is basically the sum of all the U factors. Mathematically, if you remember your algebra from a few years ago, U is 1 divided by R, and inversely, R is 1 divided by U. So U and R values are directly related. They're one over the other. So you could really give the U factor of a particular product or a particular construction and get the R value directly from that. But typically, you'll get a U factor on a product, an R value on an assembly. So there's R value of a floor, and you can see in this little house that when we design a space, you'll lose a certain amount of U factors depending on where we put that heat. So once we know that, we know how much heat to put in. And to give you in perspective, we talked about 10 watts per square foot. There are buildings in highly insulated spaces in France or in Germany where insulation is standard by building code, where we can put as little as 2 to 3 watts per square foot and actually heat the house with it. As long as you don't lose a lot, you don't need a lot to make the space very comfortable. And finally, I wanted to give you just a quick example of how we calculate it when we have to do this. When you have an R value and a U value for all the components, and you look at what's outside those walls or below that floor or above that ceiling, you can actually determine how much heat you need to put in. And that formula is actually pretty simple when you just understand it. You have an area, that wall to the bedroom, that's 18 degrees C. You have that area of 6 square meters in that instance, so about 60 square feet. There is a temperature difference between the room you want to heat and that bedroom, so you're going to lose a little bit. And then you have the U value or the R value of the U value of the wall, the R value of the whole assembly of the wall. And that gives you a total wattage loss. So in this particular example, to heat that room, we were going to lose about 2.5 watts per square foot. So what does it mean is that when we know how much wattage we need to heat that space, say 5 watts per square foot, we know we need to build a system that's 7.4 watts per square foot because we're going to lose 2.4. So hopefully that was clear enough. I just wanted to give you an idea of heat loss. If you don't remember any of this, the important thing is that when you bring heat to a space, you have to be mindful of the fact that you're going to lose heat to the floor, you're going to lose heat to the walls, and because of that, it helps you design a system. Now, if you put floor heating in a bathroom for it to be nice when you step out of the tub or the shower, you don't need to worry about that. But if you're going to use floor heating to heat a sunroom or a basement or your whole house, this becomes important and you need to seek assistance or be considerate of it. Let's talk about heat in general. Heat in general can be of 3 kinds: conduction, convection, and radiation. Once you got those 3, it helps you understand how you can heat a space. Conduction should be familiar to everybody. That's basically putting a pot on a ceramic stove or putting an object on another object. So it's basically the conduction of heat through solid materials. Your pot is a solid material and will transfer that heat to the water and boil the water. That's conduction. Convection is the transfer of heat through air or fluids. And in this instance, convection will be a good example of convections are mini splits or air source heat pumps or furnaces, where there is a motor or an engine or a source of heat that will turn cold air into warm air and then blow it into the space and then make you feel warm through heating the air around you. That's convection. And then radiation is the transfer of heat through EMF, through electromagnetic fields, electromagnetic waves. You've heard about EMF. They no longer exist with heated floors, by the way. It's something that people were worried about when I started in this business 20 years ago. It just doesn't exist anymore. There's more EMF in your phone than there ever would be in a heated floor. So before you ditch that heated floor, get rid of your smartphone, which I don't think any of us are prepared to do. So conduction, convection, and radiation are the 3 types of heating. But we'll find that a lot of the heating systems that we recognize today are a combination of these because none of them are exactly just one thing. For example, a radiator is conduction and convection, and there's some radiation as well, but a radiator is mostly conduction, as you can actually touch the radiator, you could put things on the radiator, you could put your clothes to dry on it, but it creates a convection because it heats the air into the room. That hot air will rise to the ceiling and then rotate around the room. So it creates an effect of convection through the cold air and the warm air that circulates into the space. Back a bit to heat loss. Now that we talked about it and we know the three forms of heat, how we're going to heat a space is going to directly determine by where we're going to lose that heat. If we have a lot of windows and we're going to have a lot of exposure to the outside element, heating the air in the space is a bad idea because that air is constantly in a thermal exchange with the windows. So you don't want to use a heating system that is going to be heating the air, or you're going to fight a bigger enemy than you can fight, at least cost effectively. If you have high ceilings, for example, you want to be considerate of how you're going to heat that space. And there are plenty of other reasons to choose one system or the other. We'll talk about electric floor heating, hot water floor heating, but reducing heat loss is really the first thing you want to do when you build a space or design a space. What am I going to do to actually not have to put too much heat into that space is really your first consideration. A quick example here for heated floor specifically. If you don't do anything at all, you can take up to 3 hours and a bit. That's a lot of time. No one really wants to spend that time heating a floor. Now, these thermostats are doing it for you. You don't typically have to worry about how long it takes to heat. The thermostats of most of the brands you've used today do that math for you. But why would you want to spend all that energy in doing that? Once you start adding just about a 1/4 inch of insulation, which is not a whole lot. It could be a cork underlayment. Some manufacturers have specific boards that they sell, but just at 5 millimeters, so just under a 1/4 inch of insulation, you reduce that down to 1.5 hours. So that becomes really quick. And if you double that, you're under 1 hour, you're 45 minutes. So it could be really, really quick to get to a bathroom temperature of about 80-degree floor temperature. Quick note here is that you'll see 80-degree floor temperature, but hey, hold on, Regis, I don't want my bathroom to be 80 degrees. 80 degrees is the floor temperature. That means the resulting air temperature will be about 10 degrees below, so 70 degrees. That's a typical thing between floor heat and ambient heat. There's about a 10-degree delta between the two. So that was just an example of how insulation can really help. You could see here with just a minimal input of insulation, you can actually cut your energy costs just by half. How do you select a heating system? Well, let's take a look at the various heating systems out there, because in America, 67% of homes are heated with a furnace, usually a gas furnace. And that choice has been made in part because a furnace can provide heating and cooling, but plenty of systems can provide heating and cooling. Air source heat pump, mini splits can provide heating and cooling. They're just not popular. So why is it that HVAC systems have become so popular? Well, one of the answers is that there is a huge network of installers. So it has become quite cost effective to put in a furnace. It's not expensive. And as a builder, when you build a house, there's a plethora of people who can come and do the job for you. They can come and install the furnace, put all the ductworks, and voila, you've got a heating system. So they don't second guess what the best heating system would be for the space or for the house or for the user. They put in a furnace and oversize it a bit because they know your windows are not going to be the best, and you probably don't have spray foam insulation in all the walls and ceilings and floors. And that's about the standard setup for the American builder. But we can do better than that. Let's take a quick look. All right, radiators and baseboards, similar in their approach. Radiators are typically hot water driven. Baseboards are mostly electric, although there's water baseboards as well. Radiators and baseboards are mounted on a wall on one side of the room. And what happens if you look at a thermal image of the air rotating is that right next to the radiator and baseboard, the air will warm up either because there's a fan or simply through radiation around the device. And then that hot air is lighter than cold air, and it will rise. It will rise to the ceiling, and then it will transfer itself on the other side of the room to the cold side of the room. And then it will cool down, so it will start lowering along the opposite wall and then rotate, and you can see that convection effect that I was talking to you about. So with radiators and baseboards, you have a bit of convection, you have that radiation, you have that conduction if you touch it. But the important thing is to see that the hottest part is, of course, unsurprisingly, next to the radiator. Yet, if you've ever been in a house with radiators and baseboards, they're typically installed right below the window. If you've ever been in an apartment or house that has a radiator, they're always underneath the window. I don't know why they chose that, and probably because they thought it's the coldest part of the room, so let's put two forces against each other and the radiator will fight a cold window. It's actually a terrible idea, because the immediate thing that will happen is that hot air that you've created with the energy you've spent in your radiator will immediately go out to the window. That's not what you want. That leaves only half the hot air to circulate through the room and keep you warm typically on the other side of the room because you can't put your couch against that radiator. So your couch is on the opposite side of the room. Therefore, not the most effective. It can be efficient because it can be recirculating hot water, or it could be using your existing boiler and so forth and so forth. But it is not the most comfortable type of heat because it doesn't give you a design freedom. And we'll talk about some of the benefits. Forced air systems, as we said, 67% of homes have them. They're the standard in North America for heating. Important to know if you've traveled around the world that they're not the standard at all for other people. They're not common at all in Europe. Europe has some degree of air force heat pumps. Mini splits are very common across Asia and Europe. But forced air systems like the furnaces, gas and electric that we have are not common at all in other countries. It's a very North American thing. And we have this ductwork that then pumps the hot air or cold air, but we'll talk about heat in this presentation. And we'll pump the hot air through all the rooms of the house. So there is a sense of efficiency, one, as we said, because a lot of people know how to do it, how to install it, how to do it right. But then you've got this machine, this device, this monster in your basement that turns on and off 9 times an hour, by the way, on average. A furnace turns on 9 times an hour, and then will turn cold air into hotter air and blow it through the ducts. So what will happen, whether you had heat vents at the ceiling or at the floor, it will blow that air that will rise to the ceiling, and then there will be a convection effect until wherever the thermostat is located captures a drop in temperature, and then the furnace kicks on again and replaces that cold air with hot air. Disadvantages of that: the heat is not even throughout the house. It doesn't matter how nice your house, if you have a furnace, there are rooms that are colder, rooms that are warmer, and it's impossible actually to have every room at the same temperature. So your level of comfort is limited by how well your ductwork is set. It doesn't really matter how nice your thermostat, that's more of the programming side of things. Your level of comfort is not ideal. It can be good for a few rooms, but then it's not good enough for a few others. Think about a basement. A lot of people with forced air systems complain that they can never get the basement warm enough. So that's a simple example. In my house, we have the bedroom above the garage, and we can never get that room warm enough. So there are limitations. Another one that few people know about forced air systems is that you have a loss in humidity and moisture in the air because that hot air that's being replaced actually dries up the air. So if you live in Colorado like me, you have to put a humidifier on the furnace to actually replace that. And then finally, you have underfloor heating systems, and those beautiful systems actually spread the energy throughout every square foot of the floor and then radiate up. Floor heating systems are about ineffective at about 4 feet. So it's exactly what you want. You want warm feet and a cold head evenly distributed through the room. So let's talk about those benefits so we can have an appreciation for what they can do for your project beyond the bathroom. First benefit is that design freedom we talked about. If you have a radiator or baseboard, you know you can't shove furniture or couches against it, or you have to stay away from it, so you lose a bit of space. So that's one first benefit of heated floors. There is absolutely nothing in the room. It's spread evenly, so you could put your furniture wherever you want. The second one, we just talked about it, the furnace will of course dry the air by 10 to 20%, depending on where you live. So if you have allergies, that's no good, because you don't want the air to lose a lot of moisture. And if you have allergies, you also have a lot of allergens and pet dandruff that will circulate even if you have the best filter on the market today. So a healthy indoor air quality, IAQ stands for indoor air quality, is one of the secondary benefits of heated floors because it doesn't affect the ambient air or its circulation or its humidity content. Higher comfort levels, I'll argue that, of course, everybody will root for their own horse when it comes to heating, but I'll tell you a little story about higher comfort levels and why that is important. In another presentation, we talk about how to design heating systems. We rely quite a bit on ASHRAE 55, which is a standard for designing heating and cooling systems in commercial spaces and residential spaces alike. And what ASHRAE 55 does really is help people design a comfortable solution. But actually, when you ask a lot of people what comfort is, they will give you a very subjective answer. What comfort is will be different for all the 100+ people on this call. That is not what ASHRAE means to achieve. Comfort is actually very objective when you break it down into 3 components: temperature, humidity, and air movement. If you ask anyone you know what comfort means, you will get their subjective answer. Well, I like it when it's not too hot. I like it when it's cool. I like it when it's this. I like it when it's that. But that doesn't help you design a comfort system, because if there are 4 people in the house, they'll have 4 opinions, and you can't design a system that has 4 different speeds. So you need to consider 3 different parameters: temperature, humidity, and air movement. And that will help you mathematically design a good system that suits everybody. So a quick word on that equation of temperature, humidity, and air movement. Temperature in itself means nothing. Temperature in itself is 2 guys a few hundred years ago deciding how much expansion of mercury happened in a tube when you were boiling and freezing water. That's about it. That's what temperature is. We have learned to know that 80 degrees is nice and 20 degrees is cold, but for a lot of people in the world, 80 and 20 doesn't mean anything. For them, 0 is cold and 25 is very nice. That's because we have different scales. So temperature in itself doesn't mean anything. Actually, a good example of that is that when you watch the weather forecast, they'll talk about the heat index. So what is the heat index? Well, that's the temperature and the humidity combined. Because in this little chart that you see on the screen, at 90 degrees, if it's 90 degrees where you live, and it's 30% humidity, which is the ideal level of humidity, it feels like 90 degrees. You can see the intersection of the graph in the light blue section. 90 is 90. But if it's 90% humidity where you live, if you're in Savannah, Georgia right now, 90 means 120, because a high humidity will make you to perceive the temperature as much higher than it is. That's a heat index. It's a feels like of the weather forecast. And the same thing happens on the downside. And if you live in Toronto or Chicago or New York, you'll hear about the wind chill. And the wind chill is a temperature combined with the air movement. If it's cold, that's bad enough. But if it's cold and windy, it's worse. That's the wind chill, and that's another element of comfort. So the summary of that is that a floor heating system can actually regulate the temperature without affecting the humidity or the air movement. It doesn't affect the moisture in the air, and it doesn't rotate air in the space. So it really helps you create a higher level of comfort, a more controlled level of comfort. That's why I brought this forth and tried to explain this to you. This temperature is then controlled typically room by room. If you have a whole house system, you will find yourself with 5 to 10 thermostats. That's an unusual situation if you're used to a furnace system, but actually that gives you the ability to control the system room by room or zone by zone. So if you have a water or electric floor heating system throughout the house, you will have different opportunities to control that space, both in time and in temperature. So there are spaces in the house that you don't use all the time, then why heat it? If you wake up in the morning and you go to work, at least in a prior life before COVID, you wake up in the bedroom, you go to the bathroom, you make some breakfast in the kitchen, and then you go off to work. But to keep those 3 rooms at 70 degrees, you've heated your entire house. Why? You didn't need to do that. So having a multi-zone system is really helpful in conserving energy and making it more cost-effective for you. A quick word on Wi-Fi. All the controls today are Wi-Fi, or they have a Wi-Fi option. I think it's important to differentiate the Wi-Fi. And now that everybody's Wi-Fi, how do you differentiate yourself? We'll look for smart devices that do the work for you. Wi-Fi is just a communication technology. It's not a whole lot more than that. It's great. We now have it everywhere. It's in our pockets. But Wi-Fi in a thermostat doesn't mean a whole lot if you have to open an app and do all the programming and the activating yourself. That's just remote. That's not smart. Smart is when the Wi-Fi is using information that's outside, like the weather forecast or your location, and that actually uses that information to turn on and off the system. There are systems now, as you know, with a few thermostats that can follow where you are and then turn on and off your heating based on whether you're in the house or outside of the house. That's smart because it's doing the work for you. So zoning is really an important bit of heating systems, usually proper to mini splits, air source heat pumps, floor heating, radiant systems, and eventually compatibility with renewable energy sources is a final benefit that will become more and more important as we gain access to them. They're prevalent in many parts of the country, many parts of the world, but not so much in others. It's still under 5% of our global energy supply, but it will be growing because we're going to need it. And because of that, having a heat source or cooling source that can rely on it to give you free heat or free cooling is certainly beneficial.